So let's discuss the remaining questions of surface area and volumes. So this question says that find the area enclosed by the curve in which the plane z equals to 2 cuts this ellipsoid. So the question says that they have given us an equation of ellipsoid. So first let's draw it graphically. Let's assume it has x-axis, this as y, and this as z-axis. So for example, let us assume that this represents our ellipsoid given by this equation, that is x square by 25 plus y square plus z square by 5 equals to 1. Now we are supposed to find the area enclosed by the curve which the plane z equals to 2 cuts the ellipsoid. So there is a plane given by z equals to 2. So let's assume that this is the plane z equals to 2. So when this plane z equals to 2 will cut the ellipsoid, so we will basically get an ellipse of this sort, and we are supposed to basically evaluate the surface area of this ellipse. That's what the question says. So let's do that. So it will be equals to, now when the curve z equals to 2 cuts this ellipsoid, so this z equals to 2 must satisfy the equation of ellipsoid. So from here we'll get basically the equation of ellipse whose area we are supposed to evaluate. So that will be x square by 25 plus y square plus z, that is 2 square by 5 equals to 1. So from here we'll get x square by 25 plus y square equals to 1 minus 4 by 5, which is equals to x square by 25 plus y square equals to 1 by 5. So this is the equation of ellipse whose area we are supposed to evaluate. So surface area will be basically, if I solve it from here, if I solve it for x, so it will be x square equals to 1 by 5 minus y square times 25, which gives us x square as 5 minus 25y square, that is x is taking values in between plus minus under root 5 minus 25y square. So x varies from this point, like varies in between these points, and y, when x is equals to 0, y square is basically 1 by 5. So y varies in between plus minus 1 by root 5. So let's see what will be the surface area of this ellipse. So required surface area will be equals to double integration, let's name this region as R, double integration over R dy dx. So this basically gives us the surface area. Now we need to see the limits or the range over which we need to evaluate to get the required surface area. Now if you observe that, let's say this is our ellipse and this is x-axis, and let's name this as y-axis. So if you observe that the ellipse is basically symmetrical along both x-axis and y-axis, so it is enough to evaluate area of this, like area of the surface lying in first quadrant, and then we can multiply that by 4 to get the area of whole ellipse. So this required area will be equals to 4 times of surface area lying in first quadrant. So that is basically equals to 4 times y varying from 0 to 1 by root 5 and x varying from 0 to under root 5 minus 25 y square dx dy. These limits are positive because in first quadrant, if 0 comma 0 is the center of ellipse, then x is varying from this point x equals to 0 to till here, which is 5 minus 25y square, and likewise y is varying from 0 to this point, which is 1 by root 5, basically 0 comma 1 by root 5. So this is the required integral that we are supposed to evaluate. So it will be equals to 4 integration with respect to y, limit varying from 1 to root 5 And now if I evaluate the inner integral, it will give me under root 5 minus 25y square dy, which is equals to 4 0 to 1 by root 5 integration 1 by 5 minus y square times 25 dy. Now if I pull out this 25 out of the square root sign, I'll get 20 times integration from 0 to 1 by root 5 integration 1 by root 5 square minus y square dy. Now we have a direct formula to solve this integration, which is basically integration of 0 to, let's say, like integration of under square a square minus x square dx is equals to x by 2 under root a square minus x square plus a square by 2 sine inverse x by a. Now using this result, we can evaluate this given integration. That will be equals to 20 times y by 2 under root 1 by 5 minus y square plus a square, that is 1 by 5 by 2, that is 10 sine inverse y divided by 1 by root 5, and its limit varies from 0 to 1 by root 5. So if I just plug in the limits, it will be 20 times 1 by 2 root 10 1 by 2 root 5 into underscore 1 by 5 minus 1 by 5 plus 1 by 10 sine inverse 1, and when I plug in 0, that will give me 0 only. So it is equals to 20 times 1 by 10 into pi by 2, because sine inverse 1 is pi by 2, so which is equals to pi. So the final answer or the area is pi square unit. So this is the final area of the curve that we got by cutting the ellipsoid with this plane z equals to 2. So now let's move on to see the next question. So this question says that compute the double integral which will give us the area of the region between the y-axis, this given circle, and the parabola given by this equation. So first let us draw the figure to get an idea of the area which we are supposed to evaluate. So let this be my y-axis, and let's assume that this is x-axis. So first line of the area is y-axis, that is this line. Second is a circle, so circle is x minus 2 square plus y minus 4 square is equals to 2 square. So that means center of circle is 2, 4, and radius of circle is basically 2 units. So let's see where 2, 4. So 2 lies somewhere here, and 1, 2, 3, 4. So center of circle lies somewhere here. Let me just extend my y-axis. And the radius is also 2 units. So this circle will basically be touching the y-axis. Let's assume that this is our required circle. And the parabola, that is x square is equals to 2y. So parabola is x square equals to 2y. So parabola will be passing, if you observe that parabola will pass via, so parabola will be something like this. Somewhat like this will be our parabola. Now first thing, in order to evaluate this, we need to get idea of these intersection points of the parabola and the circle. So the area we are supposed to evaluate lies in between the y-axis, the circle, and the parabola. So the basically area is this area, the area that I am shading with black color. So this is the area whose double integral we need to evaluate. So in order to evaluate that, we need to know the intersection points of the given circle and the parabola. So for that, first let's just solve these. So it will be x minus 2 square plus y minus 4, and y from equation of parabola is x square by 2. So y minus 4 square is equals to 4. Now if I just use a minus b whole square, it will be x square plus 4 minus 4x plus y square plus 4 square, that is 16, minus 8y is equals to 4. Now I can plug in the value of y from the equation of parabola. So that basically gives me x square minus 4x plus y is x square by 2 square plus 16 minus 8, x square by 2 equals to 0. That basically gives me x square minus 4x plus x raised 4 by 4 plus 16 minus 4x square equals to 0, and it simplifies to x raised 4 by 4 minus 3x square minus 4x plus 16 equals to 0, which is equals to x raised 4 minus 12x square minus 16x plus 64 equals to 0. So we need to solve this equation in order to get value of x, and then we can solve it for y using the equation of parabola. Now if I solve it for x by hit and trial method, so you can observe that x equals to 2 satisfies this equation, because 2 raised 4 is 16 minus 12 times 4 minus 16 times 2 plus 64. It is equals to 16 minus 12 times 4 is 48 and 16 times 2 is 32 plus 64. So it is equals to 64 plus 16 is basically 80, and again 48 plus 32 is again 80, which gives us 0. So x equals to 2 is basically one root of this equation. And if you observe that, like if I simplify it, it will be equals to, like let me just erase it, x equals to 2 is one root, and other we can evaluate by dividing this equation with x minus 2, that is minus 12x square minus 16x plus 64. Now I need x cube, it will be x4 minus 2x cube, and it is 2x cube minus 12x square minus 16x plus 64. So this time 2x square, it will be 2x cube minus 4x square minus plus minus 8x square minus 16x plus 64 minus 8x plus 16x plus minus, so it will be minus 32x plus 64 minus of 32, it will be minus 32x plus 64, which gives me 0. So this equation, basically this equation is equals to x minus 2 times x cube plus 2x square minus 8x minus 32 equals to 0. Now I need to solve this equation, this cubic equation, in order to get another point of intersection. But I couldn't solve it manually by hit and trial method, so I took help of an online calculator. So that gave me another root, like two roots are in complex and the real root is 3.32. So this is basically approximated root. So the 2 points where this parabola is intersecting the circle is, one is 2 and other is 3.32. Now using this equation of parabola, I'll get here my y as 2 and here 5.51. So these are the 2 points on which the parabola is intersecting the given circle. Now we need to basically evaluate the area. So for that, if you observe that, like if this is my 2 point and this is also 2, so I can draw a line, like let's say this is my parabola like this, then I can draw a line passing via the center, that is at x equals to 2. So the area of required region is basically sum of area of region that I shaded with pink color plus sum of region that I shaded with green color. So we can write it as, if the complete area is, let's say, R, then double integration dy dx over r is same as double integration over r1 plus double integration over r2, where r1 is basically region shaded with pink color and r2 is region shaded with green color. Now if you observe that the region that I shaded with pink color is basically half of the circle, because this line x equals to 2 is passing via the center, so this line will basically act as a chord or the longest chord, which is basically diameter. So I can just directly evaluate this area using, like, I can take half of area of circle, and area of circle is pi times pi r square and radius is basically 2, so pi 2 square, plus I need to evaluate this area over region R2, that is dy by dx. So it is equals to 2 pi plus integration over region R2. Now I need to see the limits of region R2. So limits of region R2 is basically, if you see that in region R2 my x is varying from x equals to 2 to this point, from x equals to 2 to this point, that is 3.32, and my y is varying from this, that is x square by 2 up till this point, which is point on the circle. So I need to evaluate y like in terms of x using the equation of circle. So if I evaluate y using equation of circle, so that will be y minus 4 square equals to 4 minus x minus 2 square, and from here I will get my y as 4 plus minus under root 4 minus x minus 2 square. But we are in first quadrant, so we'll take only its positive value. So from here it will be equals to 2 pi plus x varying from 2 to 3.32 and y varying from x square by 2 to 4 plus under root 4 minus x minus 2 square dy dx. Now if I solve it, it will be equals to 2 pi plus 2 to 3.32 4 plus under root 4 minus x minus 2 square minus x square by 2 dx. Now if I integrate it with respect to x, it will be 2 pi plus 4x, and its integration will be minus x cube by 6 plus integration of this, that is 2 to 3.32 under root 4 minus x minus 2 square dx. Now I can use here a result which we used in previous question, that is its integration will be 2 pi plus, here also limit varies from 2 to 3.32, 4x minus x cube by 6 and limit varies from 2 to 3.32 plus x minus 2 by 2 under root 4 minus x minus 2 square plus 4 by 2 into sine inverse x minus 2 by 2, and limit varies from 2 to 3.32. Now I need to evaluate this limit in order to get the final answer. So this simplifies to basically 2 pi plus 4 times 3.32 minus 2 minus 1 by 6 into 3.32 cube minus 2 cube plus, now if I plug in the limits here, it will be 3.32 minus 2 by 2 under root 4 minus 3.32 minus 2 square plus 2 into sine inverse 3.32 minus 2 by 2, and when I plug in the limit, like when I plug in x equals to 0, this whole term will be 0. So this is the final answer, and I can simplify it using calculator, like that you can do yourself. This completes the explanation part. So this is the final answer, square units, in square units. So let's move on to solve the next question. So the next question says that compute the volume of solid enclosed in between the surfaces this and this. So what they have done is they have given us basically equation of two cylinders, with one has z axis as its principal axis and another has y axis as its principal axis, and both the bases, like both cylinders bases have radius 3. So we need to evaluate its volume. We have done a similar equation, that is basically the general case. In that, equations of cylinder are x square plus y square equals to a square and x square plus z square is equals to a square. So we have done these cases. In this question they have specified specifically the values of a. So if I draw its figure, so it will be somewhat like this. This is x axis, this is y, and this is z axis. So we have one cylinder like this, and another cylinder like this. So we need to evaluate volume that lies in between, that is common in between both the cylinders. Now if you know that the cylinders are basically symmetrical around their axis, like around their principal axis, so that is like it's okay if we just evaluate the if we just basically solve the equation, like find out the volume that lies in first quadrant, that is where all the x, y and z are positives, and then we can just multiply it with 8 in order to get the whole volume that is there. So the required volume will be basically equals to integration dv, and let's name the region, like let's name the solid region as r dash, and r dash is the region whose volume we are evaluating. So it will be equals to 8 times the volume in first quadrant, because here it will be 8. So it will be equals to 8 times dz, dy and dx. Now from this equation you can see that z varies in between. In first like in this quadrant it will be from 0 to under root a square minus x square. Likewise y from here will be in between 0 to underscore a square minus x square. Now in the question they have specifically given as a square as 9, so we need to write that. So it will be under root 9 minus x square and 9 minus x square, and x varies from 0 to 3. Now if I evaluate it, it will be 8 times integration x from 0 to 3, 0 to under root 9 minus x square. Now first let's integrate it with respect to z, that will give us 9 minus x square dy dx. So it is equals to 8 times integration from 0 to 3. Now there is no y involved in this, so we can treat it as constant. So it will give us 9 minus x square times under root 9 minus x square dx. Now this is equals to 8 times integration from 0 to 3, 9 minus x square dx, and if we solve it, it will be 8 9x minus x cube by 3, limit varies from 0 to 3. That gives us 8 times 9 into 3 minus 3 cube by 3, which is equals to 8 times 9 3 is 27 minus 9, which is 8 times 18, that is 144. So this 144 cubic units is basically our final answer, or the volume that is enclosed by the given two cylinders. So let's move on to the next question. So this question says that find by triple integration the volume cut off from the cylinder, this is basically equation of cylinder, by the planes this and this. So we have a given cylinder, and if I simplify its equation, it is x square plus y square minus ax equals to 0. That simplifies to x square minus ax plus y square equals to 0, which can be further simplified. So it is x square minus ax plus a square by 4 plus y square equals to a square by 4. which is equals to x minus a by 2 plus y square equals to a square by 4. So center of this cylinder is basically a by 2 comma 0 and radius is also a by 2. Now if I just draw this cylinder like if this is my z axis like x and y, and this is my basically z axis. So cylinder is somewhat like this is x, this is y, and this is z. So center is a by 2 comma 0 and radius is also a by 2. So like this is base of my cylinder and cylinder is somewhat like this, and there are two planes, that is z equals to mx and z equals to nx, which basically cuts this cylinder. So let's assume that this is z equals to mx and let's assume that this is z equals to nx. So we are supposed to evaluate this like the volume that lies in between these two, like that line in between these two planes and inside the cylinder. So in order to evaluate that, so basically volume will be equals to triple integration dv, which is also equals to double integration, and since z varies in between these two planes, so it will be mx nx dz times dA, and dA is basically the base area, that is this area. So it will be equals to double integration, let's assume that base is represented by r, nx minus mx dA, which is equals to double integration r m minus n into x dA. Now I can just reduce it in polar coordinates form in order to get a simplified form. So in that it will be, I can assume my x minus a by 2 equals to r cos theta and y equals to r sin theta. Or I can do is, I can just assume x as r cos theta only and y as this. So from here I got equation of cylinder is basically x square plus y square equals to ax. So that basically gives me r square equals to a r cos theta. So from here I got my r equals to 0 or r equals to a cos theta. So this basically gives me limit of my r, like r is varying in between these two. And if you observe that since the base lies in like these two ordinates, so theta varies from minus pi by 2 up till pi by 2. So this will be equals to double integration theta from minus pi by 2 up till pi by 2, and r varies from 0 to a cos theta, and it is m minus n, x is r cos theta, and dx times dy will be basically equals to r dr d theta, where r is basically Jacobian because of these transformations. You can also evaluate it, but it's better to remember it for polar, cylindrical and spherical transformations. So it will be r dr d theta. So it simplifies to integration from minus pi by 2 to pi by 2. I can pull this m minus n outside the integration sign because it's constant only. So integration from 0 to a cos theta r square cos theta dr times d theta. So it is equals to m minus n integration from minus pi by 2 up till pi by 2. If I evaluate it with respect to r, it will be r cube, and theta varies from 0 to a cos theta, and we have this as well. So cos theta d theta. So it will be equals to, I can pull this 1 by 3 out, so it will be m minus n by 3 integration from minus pi by 2 to pi by 2 a cube cos 4 theta d theta. Now I can pull this a cube outside as well, so it will be m minus n a cube by 3 minus pi by 4, pi by 2 to pi by 2. I can write it as 0 to pi by 2 times 2a cube and cos 4 theta d theta, because this cos theta raised 4 is basically even function, and we have a resulting definite integral that says as minus a to a fx dx equals to 2 times 0 to a fx dx whenever this function fx is even, and it's equals to 0 when the function fx is odd. So this simplifies to, I can write this as m minus n 2 a cube by 3 integration from 0 to pi by 2 cos theta raised 4 d theta, and this is like its integration is basically, I can write it as this 2m minus n a cube by 3 into 1 by 4 integration from 0 to pi by 2, that is 2 cos square theta whole square d theta, which can be written as like m minus n a cube by 6 integration from 0 to pi by 2. 2 cos square theta is 1 plus cos 2 theta whole square d theta, which is equals to m minus n a cube by 6 and if I open this whole square, it will be 0 to pi by 2, 1 plus 2 cos 2 theta plus cos square 2 theta d theta, which is equals to m minus n a cube by 6, and this can be further simplified as integration from 0 to pi by 2, 1 plus 2 cos 2 theta plus 1 plus cos 4 theta by 2 d theta, which gives me this as like from there it is equals to m minus n into a cube by 6, and if I integrate it with respect to theta, it will be theta plus 2 sine 2 theta by 2 plus theta by 2 plus sine 4 theta by 8, and limit varies from 0 to pi by 2. So it is equals to m minus n a cube by 6, it will be theta plus theta by 2 is 3 theta by 2, so 3 by 2 into theta, that is pi by 2, plus it will be sine pi and sine 0 both are 0, so this will contribute to 0, and likewise sine 2 pi and sine 0 are 0, this will also contribute 0 only. So this is equals to m minus n a cube, this 3 balances out this, pi by 8, so this cubic units. So this is the final volume of the region that we are supposed to evaluate. So let's move on to the next question. So the next question says that find the volume of the solid bounded above by this parabolic cylinder and bounded below by this elliptic paraboloid. So it's bounded above by BDD, basically means bounded only. So bounded above by z equals to 4 minus y square and bounded below by z equals to x square plus 3y square. So volume will be basically triple integration dv, that is same as double integration over r, that is the shadow of the region, into z varies from x square plus 3y square to 4 minus y square dz times dA, which is equals to double integration over r 4 minus y square minus x square minus 3y square dA, which simplifies to double integration over r 4 minus x square minus 4y square times dA. Now from here on, now let's just first find out basically the intersection points of these two given curves, that is the parabolic cylinder and the elliptic paraboloid, in order to get the limits of y and x. So if we if they are intersecting, then z must be equal somewhere, so that gives us 4 minus y square equals to x square plus 3y square. So from here we get x square plus 4y square equals to 4. So which gives me x square by 4 plus y square equals to 1. So this is basically equation of an ellipse. So from here we get our y as, or basically our x as, x square by 4 is equals to 1 minus y square. So from here x square will be 4 times 1 minus y square. So x is in between plus minus 2 under root 1 minus y square. So this is these are the limits of x, and whenever x is 0, y varies in between plus minus 1. So the given area reduces to, if you observe that it is even, so we can use this property, so we can use this result which states that if the given function is integral, then minus a to a, if the given function inside the integration sign is even, then this is equals to 2 times integration from 0 to a fx dx. So if you observe that the function we have inside the integration sign is basically an even function, so the volume is minus 1 to 1, and x varies from minus 2 under root 1 minus y square to 2 under root 1 minus y square, 4 minus x square minus 4y square dx and dy. So it is same as 4 times integration from 0 to 1 and integration from 0 to 2 under root 1 minus y square, 4 minus x square minus 4y square dx dy. Now if we just evaluate, if we first evaluate it with respect to x, so it will be 4 times integration from 0 to 1, 4x minus x cube by 3 minus 4y square x dy, and limit varies from 0 to 2 under root, or maybe 4 minus 4y square. So if I just plug in the limits, so it will be equals to integration from 4 times 0 to 1, 4 minus 4y square times under root 4 minus 4y square minus 1 by 3 times under root 4 minus 4y square cube dy. So this thing is equals to 4 times integration from 0 to 1. It is 4 minus 4y square raised 3 by 2 times 1 minus 1 by 3 dy. So this thing is equals to 4 times integration from 0 to 1, 4 minus 4y square is 3 by 2, and 1 minus 1 by 3 is basically 2 by 3. So it will be 8 by 3 outside, and we are integrating it with respect to y. So if I assume my y equals to cos theta, so let y equals to cos theta. So from here my dy will be basically minus sin theta d theta. Now I need to change the limits as well. So when theta is equals to 0, y is basically pi by 2, or maybe so when y is basically equals to 0, theta is pi by 2, and when y is equals to 1, theta is 0. So it results in 8 by 3 integration from pi by 2 to 0, 4 into 1 minus cos square theta, that will be sin square theta whole raised 3 by 2, and dy is minus sin theta d theta. And we know that property of definite integral which states that 0 to a fx dx is same as minus integration from a to 0 fx dx. So using this property, this results in 8 by 3 integration from 0 to pi by 2, 2 cube, and it will be sin theta raised 4 d theta, which is equals to 8864 by 3 integration from 0 to pi by 2 sin theta raised 4 d theta, which is same as 16 by 3 integration from 0 to pi by 2 sin square theta whole square d theta, and this sin square theta can be written as 16 by 3 integration from 0 to pi by 2 1 minus cos 2 theta square d theta, and we can just open this whole square, so it will be equals to 16 by 3 integration from 0 to pi by 2 1 minus 2 cos 2 theta plus there will be cos square 2 theta cos square 2 theta d theta. So it can be written as 16 by 3 integration from 0 to pi by 2 1 minus 2 cos 2 theta plus 1 plus cos 4 theta by 2 d theta. Now I can just integrate it with respect to theta. So if I just integrate it with respect to theta, it will be 16 by 3 1 plus 1, it will be 3 theta by 2 minus 2 sine 2 theta by 2 plus sine 4 theta by 8, and limit varies from 0 to pi by 2. So it will be equals to 16 by 3 by 2 times pi by 2 minus, this will contribute to 0 because sine pi is 0, sine 0 is 0, and sine 2 pi is also 0. So this and this contributes 0 only. So it is equals to, this 3 balances out this, so it will be 4 pi. So 4 pi is basically the final volume of the given solid that is bounded by this parabolic cylinder and the elliptic paraboloid. So let's move on to the next question. So the next question says that find the volume of solid that lies under this paraboloid but above the xy plane and inside this cylinder x square plus y square equals to 2x. So let's just draw in the figure first and then we can evaluate it. So the figure is let's say this is our equation of, let's assume that this is our paraboloid, this is x-axis, this is y-axis, and let's assume this as z-axis. So if this is our paraboloid, then if you see that the equation of cylinder is x square minus 2x plus y square is equals to 0, and that is x minus 1 square plus y square equals to 1. So it has center as 1, 0 and radius is also 1. So it will lie somewhere, cylinder will be somewhat like this form. So we are supposed to find out the volume of solid that lies under the paraboloid and above the xy plane and inside the cylinder. So basically the region that I shaded with black color is the region whose volume I am supposed to evaluate, because if you observe that under the paraboloid, this is the area that's lying under the paraboloid, and we are supposed to evaluate it above xy axis, that is this is base, and inside the cylinder. So this is basically the region that we are supposed to evaluate. Now so the volume will be basically equals to triple integration dv. Now if you see that our z on xy plane is 0 and it is bounded above by this, so it will be same as double integration z from 0 to x square plus y square dz into dA, where A is basically the shadow of this region on the xy plane. So it will be equals to double integration over A x square plus y square into dA. Now here on I can just change it into polar coordinates. So for that, let's assume that x equals to r cos theta and y equals to r sin theta. So from here I will get my x square plus y square as r square, and it is given that x square plus y square is basically, if I just equate these two, it will be x square plus y square will be 2x basically, which is equals to 2x, which is 2x is r cos theta. So if I just equate these two, so this give me r equals to 0 or r equals to 2 cos theta, and our theta lies in between, theta varies from minus pi by 2 to pi by 2. So the integration is minus pi by 2 to pi by 2, and r varies from 0 to 2 cos theta, and x square plus y square is basically r square. and dA will be r dr d theta, which basically gives us integration from minus pi by 2 to pi by 2. If I integrate it with respect to r, it will be r raised 4 by r, and r varies from 0 to 2 cos theta d theta, which will be equals to 1 by 4 integration from minus pi by 2 to pi by 2, 2 raised 4 cos theta raised 4 d theta. So which gives me this as, like if I simplify it, 2 raised 4 is basically 16, and we can pull that out because that's constant, minus pi by 2 to pi by 2 cos theta raised 4 d theta, which is equals to 16 by 4 is 4, and if you observe that inside we have like a even function, so it is same as 2 0 to pi by 2 cos theta raised 4 d theta, which is equals to 8 times integration from 0 to pi by 2 cos theta raised 4 d theta. And we have earlier also evaluated this integration, basically this integration, so let's just use that value only. So this in this question we have evaluated it, so it is basically equals to 3 by 2 times pi by 2. So this is equals to 8 times 3 by 2 times pi by 2. So this gives us 2 as 6 pi. So 6 pi cubic units is basically the final volume of the surface that we are evaluating. This question says that find the volume bounded by the elliptic paraboloids. So they have given us equation of two elliptic paraboloids, and we are supposed to find the volume that lies in between those two paraboloids. So first equation of paraboloid is basically z equals to x square plus 9y square, and second equation is basically z equals to 18 minus x square minus 9y square. So if we see its graphical representation, so it will be somewhat of this form. If this is my z axis, this is x and this is y, so it will be like the paraboloid will be like of this form, like this one, and the another paraboloid will be of inverted form, somewhat like this. This is just a rough sketch. So we are supposed to evaluate basically find the volume that lies in between these two, that is this volume. So we are supposed to evaluate that. So in order to solve that, so required volume will be basically equals to triple integration, and if this solid region is, let's say r, so triple integration over r dv. So it will be equals to, and let's assume that its shadow on the plane will be represented by r dash. So double integration over r dash, and z varying from 18 minus x square minus 9y square to x square plus 9y square dz into dA, where A is area of its shadow on the base region. So if we integrate with respect to z, it will be double integration over r dash x square plus 9y square minus 18 plus x square plus 9y square times dA, which is basically equals to double integration over r dash x square plus x square is 2x square, and 9y square plus 9y square is 18y square minus 18 times dA. Now I can pull take 2 as common and pull that outside the double integration sign, so it will be equals to double integration over r dash 2x square x square plus 9y square minus 9 into dA. Now in order to see the limits, like where these two paraboloids will intersect, I need to equate its equation. So that basically gives me 18 minus x square minus 9y square is equals to x square plus 9y square. So that gives me 2x square plus 18y square equals to 18. So from here I got x square plus 9y square is equals to 9. So if I solve it like for x, so it will be x equals to plus minus under root 9 minus 9y square. Now in order to equate it, it will be equals to 2 times double integration over x square plus 9y square minus 9 dx dy. So x varies from minus under root 9 minus 9y square to plus under root 9 minus 9y square, and y varies from plus minus 1 to plus 1, so which is equals to, since the inside function is even, so I can use property of definite integral that states that integration from minus a to a fx dx is same as 2 times integration from 0 to a fx dx whenever this fx function is basically an even function. So using this result, I can I'll get 8 integration from 0 to 1, integration from 0 to under root 9 minus 9y square, and x square plus 9y square minus 9 dx dy. So it is equals to 8 times integration from 0 to 1 x cube by 3 plus 9y square minus 9x, integration from limit varies from 0 to 9 minus 9y square dy. So from here I'll get it as 8 times integration from 0 to 1 9 minus 9y square raised 3 by 2 divided by 3 plus 9y square, or maybe minus, I can just pull out minus sign, so it will be minus 9 minus 9y square times 9 minus 9y square raised 1 by 2 dy. Now if I simplify it, it will be equals to 8 times integration from 0 to 1 9 minus 9y square raised 3 by 2 times 1 by 3 minus 1 dy. So it will be equals to 8 times integration from 0 to 1 minus 2 by 3 9 minus 9y square raised 3 by 2 dy. So it is equals to minus 16 by 3 times, I can pull this 9 outside, so that will be 3 cube, that is 27, integration from 0 to 1 1 minus y square raised 3 by 2 dy. Now I can just simplify it. It will be 9 minus 16 into 9, integration from 0 to 1 1 minus y square raised 3 by 2 dy. So I can assume my y is equals to cos theta. So from here dy will be minus of sin theta, and when y is basically, when y is 0, theta is pi by 2, and when y is basically 1, theta is 0. So from here it will be equals to minus 144, integration from pi by 2 to 0 1 minus cos square theta, that is sin theta square into 3 by 2, and dy is basically minus sin theta d theta. So that simplifies to minus 144, integration from 0 to pi by 2 sin theta raised 4 d theta. And in earlier questions we have seen, we have calculated this exact value, and if I see that we can use this exact value from previous questions, so it is equals to 3 by 2 times pi by 2. So if I plug in that value, so it will be equals to minus 144 into 3 by 2 times pi by 2, so that is equals to minus 72 and 36, so it is minus 36 times 3 pi. Now there shouldn't be a minus sign in answer. Okay, so we have plugged in these limits as opposite, because if you see that z varies from this point up till this point, so this should be the lower limit and this should be the upper limit, and we have reversed their roles, so there should be negative sign here, and negative, likewise negative, and a negative sign, and then it will be positive. So it is plus 36 times 3 pi. So this completes this question. Let's move on to see the next question. So this question states that calculate the volume cut off from this sphere by a right circular cylinder given by this equation. So let's first see what it represents graphically and then we can solve it. So there is a sphere with center 0, 0, 0 and radius as a. So let's assume that this is our equation of sphere and there is a right circular cylinder with z axis as its principal axis. So let's assume that this is our cylinder basically. This is z axis, this is x and this y. So we are supposed to calculate the volume cut off from the sphere by this cylinder. So basically we are supposed to evaluate the common volume in between this sphere and the cylinder. Like we don't know what exactly is our B and our A. Our cylinder can be somewhat of this form as well. That depends on value of B and A. Then the common volume will be basically the volume of sphere in that case. So it can be anything like the outer cylinder or the inner cylinder based on the values of A and B. So we'll solve it generally without considering which one is greater or which one is less. So let's solve in this question. So the required volume will be equals to volume triple integration. If the common area, let's assume it as R. So triple integration over R dV. Now from the equation of sphere, that is x square plus y square plus z square equals to a square. So from here z square will be equals to a square minus x square minus y square. So z will be equals to plus minus under root a square minus x square minus y square. So the required volume will be double integration over, let's say, region R dash, and z varies from minus a square minus x square minus y square to under root a square minus x square minus y square dz times dA, where R dash is basically its shadow on the base plane. So it will be equals to double integration R dash 2 times under root a square minus x square minus y square dA. So it is equals to 2 times double integration over R dash under root a square minus x square minus y square dA. Now let's just convert it in polar form in order to simplify our calculation. So let's assume that x equals to r cos theta and y equals to r sin theta. So from here our integration will be 2 times under root a square minus r square and dA will be r dr d theta. Now if we just simplify the limits, theta will vary from 0 to 2 pi and r will vary from basically 0 to basically b, that is radius of cylinder, because the volume that is common in between depends on radius of cylinder, not on the radius of sphere. So because like if it is this cylinder inside one, so this is the common area that we are evaluating volume on. So it's r varies from 0 to b, so it will be equals to 2 times integration 0 to 2 pi integration 0 to b r underscore a square minus r square dr d theta. Now what I can do is I can assume this a square minus r square as some term u square. So it will be minus 2r dr equals to 2u du. Now if I just change the limit, it will be equals to 0 to 2 pi and integration from when my r is 0, u is a, and when my r is b, u is basically under root a square minus b square, and from here r will be okay. So from here I'll get r dr is equals to minus u du. So r dr will be minus u du and it will be under root u square minus u du d theta. So it simplifies to 2 times integration from 0 to 2 pi 0 to under root a square minus b square minus u square du d theta. That simplifies to 2 times integration 0 to 2 pi minus u cube by 3 and u varies from 0 to under root a square minus b square d theta. That gives me 2 integration 2 pi, like we can just integrate it with respect to theta because the term inside the integration sign is constant only after substituting the limit. So it will be 2 times 2 pi minus 1 by 3 into a square minus b square raised 3 by 2. So it is equals to minus 4 pi by 3. Oh, it is, this limit is a not 0. This one is a. So it will be minus 1 by 3 times plus 1 by 3 a square, or a cube basically. So that simplifies to minus 4 pi by 3 into a square minus b square raised 3 by 2 minus a cube. Minus a cube, which is equals to 4 pi by 3 a cube minus a square minus b square raised 3 by 2. So this is basically the final answer, or the common volume in between the cylinder and the given sphere. So it's in cubic units. So this completes our questions on double integral. Tomorrow we'll see some basically questions on surface area and volume. So tomorrow we'll see some miscellaneous questions that were asked in calculus, and then that will complete basically our calculus portion. Oh, there will be one more video regarding the 2025 questions that were asked related to calculus. So post that we'll complete our calculus part. So thank you for watching, and please do like, share and subscribe the channel.